Charlie, it's yours for intro.
It's my pleasure to introduce our first speaker today, Steve Presse. Steve, please tell us about your living histories.
Okay, well, thanks everyone for being here. I'd like to thank the organizers, Shri in particular, who invited me, and the generations of students who made a lot of this possible, a lot of this work possible. So I was born on the eastern part, the French part of Canada in Montreal. For those who don't know, Montreal is an island that's surrounded by the St. Lawrence River. And by talking, and I'm from actually this part of Montreal, and by talking to folks over at conferences, I found out that Julie Bettine is from here, and Jacques Shostak went to school, the Nobel laureate went to school here. So it's quite a coincidence in this west part of the island of Montreal. As far as the eye can tell, on my father's side, my ancestors came from France and settled in New France in the 1600s, somewhere between Quebec City and Montreal on the south shore of the St. Lawrence. My mom's side is a little bit more complicated. My mother's father is of Syrian and Armenian Catholic background, and his ancestors moved to Egypt in the late 1800s. My mom was born in Egypt, her father was born in Egypt, and the great-grandparents were not too sure, but we don't think so. My grandmother's side, on my mother's side, is the same. They moved from Italy to Egypt. My grandmother was born in Egypt, as was my mom, and settled for opportunities there. But, as with many ethnic or religious minorities in the Middle East, they had to flee. And in the 70s, they moved to Australia, Brazil, and Canada. The situation must have been sufficiently dire for my grandparents to ship out my mom and my uncle first to Canada. My mom pulling her out of high school when she was 16. She then worked as a cashier at the age of 17 and later went to school when we were in high school, later to become a French teacher. Well, my grandparents settled their business, their life in Egypt, and eventually emigrated to Canada as well. So what this provided us was sort of a cornucopia of languages, which was not so uncommon in the Middle East anyways, that we spoke at home. At any given point, there could be as many as 4 different languages that we spoke with each other, and different people spoke different languages to others. And what we may have lacked in terms of scientific education, or just a general knowledge of science, I think my family had in terms of emphasizing culture, reading, history, music. So on the left is kind of a little picture that I drew as a teenager of some kind of nativity scene. And then on the right is Bach. At the top is piano, at the bottom is violin. And those are the things that I kind of enjoyed. And a lot of emphasis, again, was placed on sort of understanding. It could be sort of understanding events based on historical causes, but that was always sort of a fundamental sort of underpinning. So, chemistry attracted me because there was kind of simple explanations for the world around us from atomic number and from valence electrons. You could sort of predict physical properties of the world around yourself. My disillusionment maybe came from organic chemistry, where there was a lot of arrow pushing. And the organic professor once said in response to a question of mine, well, these arrows are just pictures. We don't really know what's going on. That's quantum mechanics. So at that point, I said, well, then I need to learn quantum mechanics. And by the time I got to graduate school at MIT, I decided that I would take the graduate sequence or part of the graduate sequence in physics. And I had not taken an undergraduate course in physics yet. So that came as a bit of a shock. This was the first problem of the first problems. I didn't use this funny word. I turned to my friends and I said, I might have a question regarding gouges. And they told me, no, they're pronounced gauges. And at that point, I knew I was in for a wild ride. Well, my PhD advisor was wonderful, Bob Silby, and he was Dean of Science during the bulk of my PhD. And with him, I wrote sort of plausibly long, plausible looking long equations to describe various chemical kinetics in condensed phases. And I was able to fool some of my colleagues into thinking some of these things could be real. Here's my friend Justin Hotchkiss and his acknowledgments in his PhD thesis. Steve was able to translate our temperature isotope data and life in general into mathematical equations. But, classical sort of physics or chemistry education still left me wanting because a lot of it was based on building models and making predictions and then comparing to data. And in my mind, that paradigm never worked. Again, it may be from my childhood, I would look at things and then you try to explain try to find causes based on what you saw. Again, it could be in the context of history, but it didn't, classical sort of education in the science didn't quite match my sort of inverse modeling thinking at that time. For example, if I gave you a spacing between energy levels, can you predict the energy eigenfunctions? That's always how my brain worked. But I didn't have the sophistication or the language to sort of integrate that thinking into science until I started doing a postdoc with Ken Dill at UCSF, where I learned about likelihood-based methods, Bayesian methods, information theory, sort of culminating in a nice reviews of modern physics that I published with Ken with the sort of summary of my work as a postdoc. So I may make the whole trajectory sound quite linear so far, but there were some nonlinearities. Midway through my PhD, midway through my postdoc, my PhD advisor passed away. That was quite a shock to me. Simultaneously, my postdoc advisor moved from the West Coast, UCSF, to the East Coast to head the Laufer Center over at Stony Brook. He was very nice and offered me to come. For personal reasons at the time, I couldn't. But in the meantime, he introduced me to Carlos Bustamante, who was collecting single molecule data. And with the tools I learned from Ken, I was able to apply them sort of to that single molecule universe. And that sort of led to my first faculty position and kind of a little change in my research direction towards the end of my postdoc, publishing two important papers. The first one sort of immediately led to, I was able to spin into a funded project. The second one was sort of an unmitigated disaster because it's almost certainly wrong. So I thought, living histories is also failures and how to turn lemons into lemonade cocktails or lemonade old fashions. I don't know. So I can tell you, now I can turn a little bit to science and tell you what happened. So the thought was that enzymatic reactions that carry out, enzymatic reactions can evolve heat, and that heat needs to be released somehow. And there was a thought in the literature that perhaps this could give rise to some kind of enhanced diffusion of the enzyme in order to dissipate that heat. And people still work on this problem, I should say, despite my concerns. And one way to monitor this was to look at sort of molecules diffusing through a confocal spot. In other words, labeled enzymes diffusing through a confocal spot. And the thought was that by looking at the correlation in the photon arrivals, you should be able to say something about the diffusion coefficient. Now, in principle, if a molecule is diffusing very quickly, a labeled enzyme is diffusing very quickly through that confocal spot, the photon arrivals should be very decorrelated. And what we had noticed was that as you increase the amount of substrate, then the molecules tended to show more decreased correlation between the photons. What was not completely apparent to us was that the enzymatic reaction product may be interacting with the dye, and that could be misinterpreted as enhanced diffusion. And somewhere at the back of my head, while we were doing all this, I was really wondering, why are we correlating the photon arrivals? This is a method called FCS, and it's existed since the 70s. So it had a long sort of storied history. But I was thinking the statistics of photon arrivals should be different from diffusion as they would be from photophysics. So I should be able to analyze a couple of these photon arrivals directly without correlating them and deduce sort of diffusion coefficients. The challenge was that sometimes many molecules can diffuse into the spot. And when that happens, the photon arrivals look more decorrelated. So then this led to a sort of kind of paradigm shift, which is that the more molecules you have, the more decorrelated you look. And therefore, your estimate for diffusion coefficient seems to depend on how many molecules you have in the spot. And that kind of led to the paradigm that we focused on then for the next 10 odd years on Bayesian nonparametrics, which is to learn models and learn parameters simultaneously from data. In this case, to learn how many molecules we have and learn their diffusion coefficients simultaneously. And that at this point led to some nice papers, which then led to resources and freedom to explore more ideas and my move 4 years later as associate professor to ASU. Ideas including tracking, fluorescence lifetime imaging, FLIM, structured illumination, SIM, adaptive optics, AO, and single photon array detectors, work on single photon array detectors with collaborators from across the world. Just to give you an idea of a paper we just posted to the bioRxiv, here's an array of single photon detectors. And from the spatiotemporal correlations of those photon arrivals, we can deduce trajectories of labeled molecules in a way that's not at all apparent at this point by simply looking at it by eye. I've only highlighted a few of my I should say, and learning from all these collaborators, we've put all of sort of our insights into a textbook, which we recently published. And I've highlighted a couple of collaborators, but over the last 2 years, we've had a large number, all of whom sort of have been, in some sense, indirect mentors and have taught me different ways of approaching science. So science really sort of is a collective activity. Okay, since this is a little bit about students as well and sort of talking about academic life lessons, I thought I would end with a few of those. These are my opinions, not necessarily true, but it's what I've come to appreciate. So I think academic life lessons: be ambitious, be a voracious reader, understand first the work of others, and then only if needed, criticize constructively to find a path forward in order to innovate in a particular scientific direction. Another important one: don't internalize or dwell on any failure, move forward. In fact, actually, with the plethora of journals out there, everything's a numbers game, both grants, papers, you get a paper rejected in the morning, you resubmit it, shortly thereafter. That's no big deal. You don't internalize. This is an important one. Network, but don't overexpose yourself. Foster a strong reputation based on your scientific contributions, not your opinion on current events or societal tendencies. And finally, maybe my last one: everything is interesting. And I'm not one of those scientists who necessarily says, well, I was always interested in the human body and curing, cancer. I wasn't. I'm just interested in understanding things. And I find history just as interesting as music, and in some sense, just as interesting as my science. Focus, but not too much. Keep your interests broad. And with that, thank you.
Great. Thanks for a fantastic talk, Steve, and I'm applauding on behalf of the audience. First question is, relating to this story that you told about in this publication on looking at the heat from catalytic turnover. After you had come up with that and then started thinking about the problem and moved in this area of the Bayesian nonparametrics, what challenges did you find in communicating that shift in your thinking, to other people in the field?
Um, So the error was not discovered by me. It was later discovered by experimentalists. It was discovered with one of the 3 to 4 enzymes that we had looked at. So the others, I think, are okay. People keep working in the field, although there's been no clear explanation, scientific explanation as to why enzymes may exhibit this behavior if they do at all. In terms of my shift to nonparametrics, I would say in some sense it was inspired by that problem in order to solve, in order to analyze the photon arrivals directly, but I wouldn't say that it necessarily tied back to that field at that point.
Okay, great, thank you. Thank you. I'll pass it back to Sri now.
Steve, I wanted to ask you a somewhat lighthearted question, which is that based on 2 data points, you unfortunately lost your PhD advisor while you were doing your postdoc, and then you had to change plans when your postdoc advisor moved. Did you feel that you developed a sense of independence somewhat unusually early? And did that lead to some more lighthearted moments while interacting with others?
Maybe. I would say, my PhD advisor was Dean of Science, but he was still kind enough to meet us on a semi-regular basis. And while my postdoc advisor moved, he was always very kind. He offered us, all the lab to follow him along. And like I said, for personal reasons, I couldn't, but he was also kind enough then to say, okay, well, then stay and I will keep supporting you. So in some sense, it was as smooth as it could be. And yeah, it did develop a lot of independence, but I wouldn't say that, not being embedded in a lab is necessarily a good thing. I still sort of strongly encourage my lab today to keep talking very often to each other and to sort of to optimize their own mutual face time. I think it can be a little bit challenging to be sort of locked in a room and try to solve problems by yourself. I think there is some value in trying to, get out of your local optima in that sense.
Thank you so much. On behalf of the audience, I'm clapping and I'm closing the recording. Just give me one moment.